All right, Bill, we'll try to do our best. Thanks very much, and good morning, everyone. The last several years have seen the construction of several new decadal survey processes by the NRC and the space sciences. Everyone here, of course, is familiar with the planetary sciences decadal, the basic results announced last March. The heliophysics decadal is underway as we speak, chaired by my colleague Dan Baker at the University of Colorado, and that's due out this next spring. First out of the gate, however, was the astrophysics decadal called New Worlds, New Horizons in Astronomy and Astrophysics, and the initial results were announced just about a year ago, last August. What I'd like to do today is to talk about some of those recommendations, particularly those that are relevant, and there are some substantial ones relevant to astrophysics and science in general from the moon, particularly recommendations that have to do with the very early universe and low-frequency observations from the moon, and also in the fundamental area of gravitation using lunar laser ranging to fundamentally constrain models of gravitation and general relativity. So the New Worlds, New Horizons decadal review was led by Roger Blanford from Stanford University, and there were literally hundreds of astronomers who were involved in working on this in various panels. There was two groupings of panels, fundamentally, one called Science Frontiers and the other one called Program Prioritization. And as the Science Frontiers name imply, 5 different areas of broad scientific interest to astronomers and astrophysicists. And in red, I've listed those that have recommendations that I'll talk about today that are relevant to astrophysics from the moon, namely cosmology and fundamental physics and galaxies across cosmic time. In the area of program prioritization, that's really defining the next generation of missions or telescopes or observatories on the ground and in space. And 2 of the panels have relevant recommendations. I'll talk a little bit about today, electromagnetic observations from space, and the panel on particle astrophysics and gravitation. So looking at the broad recommendations to come out of New Worlds and New Horizons, in the science area, among the recommendations, not surprisingly, is advancing the discovery. And by this they mean applying new technologies, observing strategies, new theories that will be fundamentally transformational to astrophysics and to our science. I'm going to argue today that both what we can do at low radio frequencies in the early universe and with lunar laser ranging to probe in unprecedented fashion models of gravitation, that science is quite transformational. And then secondly, origins is once again relevant to us in talking about the moon, because here you're talking about, for example, the formation of the universe as a whole, and very importantly to us, the first stars and galaxies. Space projects, among those that were recommended, I want to point out the recommendation about enhancing the Explorer program. And I'm going to talk just a little bit about 2 missions, 2 possible missions that could utilize this Explorer category. These are missions in the vicinity of the moon. So among the science objectives, interestingly, there were only 3 broad science objectives that were defined that you see here. One is called Physics of the Universe, another was called New Worlds, that's basically exoplanets, and the third one is something called Cosmic Dawn. And I want to dwell on that just a little bit more now. What does Cosmic Dawn mean? Well, this is the definition right from the decadal survey, searching for the first stars, galaxies, and black holes in the universe. And quoting directly from the decadal, they posed it really in the form of a question. When did the first galaxies form out of cold clumps of hydrogen gas and start to shine? In other words, when was our cosmic dawn? And they talk about this activity having taken place in roughly the first 500 million years after the Big Bang in the universe. And the fundamental structures that emerged out of the cosmic dawn are the structures that today exist as galaxies, as stars, as planets, and ultimately as life. So this is a pretty fundamental first step in understanding why we are here today to some extent. This period of bursting of new stars, galaxies, resulted in a phase transition in the universe, going from an all-neutral to an all-ionized intergalactic medium that we have today, referred to as the epoch of reionization. The decadal goes on to recommend that astronomers must now search the sky for these infant galaxies and find out how they behaved and interacted with their surroundings. And it's that interacting with their surroundings that we have some unique probes of low-frequency radio telescopes that can fundamentally comment on this in the vicinity of the moon. Well, let me step back just for a moment and talk a little bit more about this era, about this process. Here's a cartoon picture that we've put together that really talks about a brief history of the universe, with the Big Bang over on the left-hand side. Today's universe would be over on the right-hand side. The Z's here represent redshifts, if you like to think in that space. If you like to think in terms of times, the T's here are times since the Big Bang. And tracing this across, you can see this is logarithmic in time. The first observations of the universe occur at about 400,000 years after the Big Bang. This is the so-called epoch of recombination. This is when the first atoms form, when electrons and protons combine to form hydrogen atoms, and it's the first time that the universe is transparent. And it produces something called the cosmic microwave background, and that's been observed by the COBE satellite. The Nobel Prize was awarded for that work, and today also with satellites like Planck. Following this epoch is something astronomers now call the cosmic dark ages. And it's dark because the usual sources which illuminate the universe don't exist yet. That is, this is before the first stars and galaxies form. Now, that doesn't mean there's nothing going on. There's a lot happening during this epoch. Overdensities of hydrogen and dark matter, which emerged from the inflationary epoch of the very early universe, are collapsing and working their way into forming those first stars. When those first stars do turn on, roughly a couple hundred million years after the Big Bang, the models predict that these stars are going to be very massive, 100, maybe more solar masses. They'll go through their lifetime very quickly, explode as supernova, and produce hot bubbles of ionized gas that you see in this cartoon picture. Those bubbles are very important for the later evolution. Shortly thereafter, the first galaxies form, and possibly at the cores of those galaxies, we now think today black holes form very early, the first quasars, and around those quasars are accretion disks which heat up and emit X-rays. We think today now, theoretically, those X-rays are as important as the ultraviolet light coming from the first stars in heating and ionizing the intergalactic medium. This process continues on. You get more and more of these hot bubbles are formed as more and more of the stars have collapsed. Eventually, these hot bubbles start touching one another. We've dubbed this the hot bubble-dominated epoch of the universe. That results in this final phase transition of going from a neutral to an ionized gas, which is completed, we believe, at a redshift of about 6 or so roughly 1 billion years after the Big Bang. Now, very importantly, virtually all of this in the red region is theoretical. We have almost no observations to speak of in this period. This is why the decadal recommended this as virgin territory for discovery, and why we can utilize lunar-based telescopes to probe this using neutral hydrogen. Fortunately, nature has provided us with a tool to probe those dark ages in the cosmic dawn, because neutral hydrogen has a phase transition, has a transition which occurs in its spectrum in the ground state that produces a line at 21 centimeters. Here is the energy level diagram of neutral hydrogen. This is the first excited state, the second excited state, and the F1, the F equals 1 and F equals 0 you see here are the two hyperfine levels that are produced in a cartoon sense by the fact that the electron and the proton both have spins. When those spins are parallel to one another, that's the high state. When they're anti-parallel, that's the low state. and that transition from one to the other will produce a photon at 21 centimeters or 1420 megahertz. Now, because we're observing in the very early universe, those wavelengths have been redshifted and the frequency is reduced so that, for example, at a redshift of 10, a little bit before reionization completes, the frequency of that 21 centimeter will be at 130 megahertz. At a redshift of 50, well within the dark ages, we're down to a frequency of 30 megahertz. So you can see that these observations of that neutral hydrogen in the early universe are going to happen at very low radio frequencies. This leads us to the moon. Up in the top here is the frequency allocation on the ground between 30 megahertz and 100 megahertz. And it's encoded for, in colors for various different things. In yellow is the frequency allocation for radio astronomy. You got about a megahertz worth of bandwidth in here. You've got broadcasting, you've got mobile phones, you've got satellite transmissions rather. It's a pretty crowded region up over here. And really polluted. We've managed to pollute the Earth pretty well with that. On the other hand, we know that the far side of the moon is radio quiet. We know that for a fact because NASA flew the RAE-2, the Radio Astronomy Explorer 2 satellite in 1973 in orbit of the moon, and here's data from that mission. This is what's called antenna temperature. Think of that as flux versus time. This is data when the spacecraft was above the near side, when the Earth was in view, and particularly below 10 megahertz, the Earth is a prodigious source of radiation, including auroral kilometric radiation. When the spacecraft was on the far side, nice, flat, low emission spectrum at the level that you expect from the galactic background. So the moon is the ideal place to conduct these kind of observations. Contrast that to the Earth. These are observations in this relevant frequency band by our collaborator Judd Bowman, who took these data in Western Australia, one of the most quiet places on the Earth. This is flux versus frequency between 100 and 200 megahertz. The blue are satellite transmissions, particularly DOD. And you can see that band is pretty crowded and polluted with satellite transmissions. So there's virtually no place on the Earth you can escape this. Well, I mentioned at the very beginning that one of the recommendations from the decadal was an augmentation of the Explorer program. The decadal talks about the Explorer program enabling rapid responses to new discoveries and provided platforms for targeted investigations, and they went on to recommend a specific enhancement in the program. That has now happened. John Morse has taken this recommendation seriously. He heads astrophysics at NASA headquarters and has put this in his budget. This is relevant to us because we've got a couple of possible missions that will be able to probe some of these recommended science areas in the decadal. I talked the other day, the first day of the conference, about the Dark Ages Radio Explorer satellite mission that would probe that epoch of star formation. In a little bit, I'll talk about a second possible mission, a lunar laser ranging retroreflector for the surface in a modest mission. All right? Well, what all of this has done is it's led us now to the construction of a roadmap that will allow us to probe these fundamental questions raised by the decadal. We've started now over this last decade with a series of ground-based telescopes to help us understand the technology, the receivers, the calibration, and frankly the limitations from observing from the ground. This has led us then to propose the experiment I talked about the other day called DARE, the Dark Ages Radio Explorer, that is under review now. And DARE will do an all-sky probing of the spectrum of the 21 centimeter signal. And theoretically, that spectrum is expected to have a number of features within them that are related to the first stars, the first galaxies, and the first black holes. So we will be able to pioneer observations at these unprecedented redshifts. That then we hope will lead down the line to an array on the far side of the moon. This is a picture, a cartoon picture in the Tsiolkovsky crater. With such an array of dipole antennas, we'll be able to not only further understand, but to map the spatial structure that's expected in the 21 centimeter and to probe further into that epoch of first stars and first galaxies. So to conclude this section on the cosmic dawn, what the survey said, radio astronomers are constructing telescopes that will tell us when and where the first stars in the universe formed. And that's exactly what we're about, and exactly why we believe the moon is the unique place to be able to do that. There's also very important additional science, or dual use science, that can be performed with these radio facilities on the moon. My colleague Joe Lazio has been working for several years and thinking about probing the lunar ionosphere using a technique called rheometry. The NRC report on the scientific context of the exploration of the moon pointed out how important and how poorly understood the lunar ionosphere is right now. There is some data that you see here from Luna 19 and Lunar 20, but there's a great deal of variation from day to night. We don't really understand or have it very well constrained. A radio antenna on the surface of the moon can probe this very easily, because on the surface of the moon, operating at below a megahertz, we can sweep through the frequency spectrum. The galaxy is a very strong source. So when we reach the stage of the plasma frequency ionosphere, the signal will cut off. That plasma frequency is directly related to the density. So we can determine very easily then what the density is. This is a technique which is used on the ground. So it's a nice example of dual use science. Another example, which we think is very exciting and very new, is from our co-eye Justin Casper on the lunar team, using these radio arrays as detectors of nanometer scale lunar dust. Recently, and this was discussed the other day, the Stereo spacecraft has detected nanoscale dust using its two electric field antennas. This picture is a comparison between a model and the observations of that dust. Extrapolating that forward to the kind of first generation arrays on the moon that we would put out there with total surface area of about 1,500 square meters, we extrapolate that we can detect about 1,000 of these dust impacts per second. Why is nanoscale dust important? A couple of reasons. Even though the particles are small, they're traveling very fast. They're traveling at the solar wind speed. Therefore, the kinetic energy onto the surface is very high. This may be an underappreciated component of weathering of airless bodies such as the moon. So we have a fairly unique way, a powerful way of being able to probe that component of the interplanetary medium. Let me switch gears in the last part of my talk and discuss gravitation. And these recommendations come from the Decadal Panel on Particle Astrophysics and Gravitation. They made some very strong statements in that panel about lunar laser ranging, indicating, for example, that laser ranging was one of 3 techniques that have uniquely detected one of the principal predictions of general relativity, that is this frame dragging effect called the lens theory precession. Also, they note that lunar laser ranging has provided the best limits to date on change in Newton's gravitational constant. If that does change with time, that breaks with general relativity. And similarly has placed the best limits to date on the strong and weak equivalence principles. That is, the equivalence principle says that a accelerating rest frame is equivalent to a rest frame in a gravitational field according to relativity. Breaking that would also break general relativity. So the panel goes on to state that a new lunar laser ranging program, if conducted as a robotic mission or an add-on to a manned mission, offers a promising and cost-effective way to test general relativity and other theories. It says these tests of the core foundational principles of general relativity. Any detected violation would require a major revision of current theoretical understanding. So these are in many ways the best probes that we have of relativity. So they go on to suggests replacing the current retroreflectors with a next generation. And our lunar team has been very much working along those lines to advance this area, both with observations of the current retroreflectors as well as designing new ones. Our co-investigator Tom Murphy, part of our lunar team, has done some remarkable work this last year using the Apache Point Observatory, which is equipped with laser ranging. It's a 3.5 meter telescope in southern New Mexico, and you see right here the green laser pointing towards the moon. The exciting result was with the recovery of the Lunokhod 1 site by LROC. Here's a picture, and that Lunokhod 1 also had a retroreflector on, that Tom was able to laze to it and find that it was able to recover a signal. But two interesting things emerged. Number one, that the position, according to LROC, was not where Lunokhod actually was. There was a 100 meter lateral offset, suggesting that the coordinate system that we currently are using on the moon has a significant offset. That's very important. That's important both for future human exploration as well as lunar science. Laser ranging can really pin this down. Secondly, this return signal is very strong. It's as strong as the strongest one to date, namely from Apollo 15. And it also has a new lever arm, which will mean an ability to much better determine libration and therefore constrain the fluid core of the moon. Tom tells me that this is a slam dunk in the next few years, that he will have some new important constraints on that fluid core of the moon. So that complements very nicely the timing with Grail also being launched to probe the interior. We're also working on new hollow cubes that Stephen Merkowitz at Goddard, one of our team members, new generation of retroreflectors that we would like to place on the moon. And then similarly, also making some advances on gas-assisted drilling. You remember the Apollo astronauts had a great deal of time drilling. Why is that important for lunar laser ranging? Because the surface temperatures on the moon change. We want to anchor it to thermal stability. So our team has been working with Chris Stackney and Honeybee Robotics. And Ricky, if you can play this little movie that's right here, can you hit that? There's a little movie right in here. There you go. You can see the effectiveness of this new drill. This is in sand, but they've also tested it in vacuum. They've tested it at Mauna Kea in compacted soil conditions. My colleague Doug Curry has been working with some of the Google X Prize teams to carry one of these drills and a retroreflector, as well as looking at the same kind of design for an Explorer mission. So let me go to summary and conclusions. I think the decadal survey, the Astro 2010 decadal survey, said some very important things with regard to astrophysics, particularly this area of cosmic dawn. When and how did the first stars and galaxies form? We can uniquely address this mystery with low-frequency radio telescopes, both in lunar orbit and on the surface of the moon. And secondly, the lunar laser ranging, again quoting from the decadal, will test the core foundation principles of general relativity, and especially with the next generation of retroreflectors and new drilling technologies that we're looking to put into place. Thanks, I'll stop there.
We have a little bit of time for questions right for that.
One very quick one, and actually it's more of a comment. In the decadal survey, one of the foci is understanding extrasolar planets, and I think the primary focus for that is really trying to find a terrestrial planet near in the solar neighborhood. But if you take a broader view of that, and Bill Botke doesn't know this is coming, but I'll advertise that his team is doing a lot of very interesting work on trying to understand the formation of the Earth's moon that has potential implications for extrasolar planetary systems and how they have been forming and how we see the broad diversity. So somewhat apologies, Bill, it's only slowly percolated into my own consciousness that some of this very interesting work on understanding how we have a moon may actually have a much broader implication and perhaps should be included in future talks such as this.
Other questions?
Yes, Wanda Davis, NASA Ames. I apologize in advance, naivety and out of my field. And I haven't read your Astro 2010 Decadal Survey. So the question I put before you when I see an array on the surface of the moon is whether it's done robotically as a technology demonstration or with humans. It brings to mind a very strong emphasis necessary for space biology, and I'm wondering if you will address that question, please.
I don't know about the biology part, but in terms of the deployment, we've been looking at scenarios that are both robotic as well as human-assisted. We've got some posters. Some of our students have been working very hard on how we would deploy this with rovers, both high school as well as some of our university students in vacuum. And also been working scenarios with ESMD on how we might do this with human assisted. So I'm not sure I got the connection with the biology part, though.
The biology, is this working? The biology I'm referring to is humans on another planet, I'm referring to the moon, for a long period of time,
Gotcha.
And what that's going to do to the human system itself. Doesn't it take a long time to put that array there?
It depends, because we have initial arrays which can be set up very quickly. We've got designs in the next few years with just a few elements that we would like to lay out with landers that would be prototypes. The ultimate array on the far side, you are right, will take some time.
That's what I'm talking
deploy.
about.
But I think there you would do that mainly robotically.
So you are going to do it robotically. Thank you.
Yeah.
Yeah, we're out of time, so I encourage everyone to knock over your neighbors and run to the next room to make sure you get there on time.
I'm sharing one of the next sections too, so I better